Okay, I guess we can start for today now. So it's my great pleasure to welcome Professor Gabor Lugosi to speak at this event. He's highly regarded researcher and a great speaker. We were very keen to have him visit us in 2019 for our first event on program on advances in applied probability. That didn't quite work out for logistic reasons, but we're very happy to have him this time, and we hope to have him in India soon when things normalize. I'll just speak very briefly about his background. So Professor Lugosi is an ICREA research professor at Pompeu Fabra University in Barcelona. His interests include the theory of machine learning, combinatorial statistics, probabilistic inequalities, random graphs, and random structures and information theory. His PhD is from Hungarian Academy of Sciences, from Science. He's on the editorial board of many prestigious journals, including Mathematical Statistics and Learning, Annals of Applied Probability, Probability Theory and Related Fields, Journal of Machine Learning and Research. And he's written many books which have become popular in the learning and probability community, foremost being Prediction, Learning, and Games. One way for me to measure popularity of a book is how often I lose it to the students. So this particular book, I've lost it twice already. It just doesn't come back. Concentration inequalities, a non-asymptotic theory of independence, combinatorial methods in density estimation, a probabilistic theory of pattern recognition. So many of you, I'm sure, have seen some of these books. They're all excellent. So Professor Lugosi, we look forward to your talk. You'll be speaking today on root finding and broadcasting in random recursive trees. The screen is yours.
Thanks so much, Sandeep, for the nice introduction. I really hope that we can do this in person next time. But until then, well, we're doing what we can. So let me try to share my screen. Let's see. Here it is. Yeah, can you see this? Can you see my screen?
Yes.
Okay, thank you. So, I'm going to talk about root finding and broadcasting in random recursive trees. I will explain what this is. This talk is based on two papers, one with Sebastian Vivek, who is at Microsoft Research, and Luc Devroy, he's at McGill University. And the second one with Luigi Dario-Berri, he's also at McGill, Luc Devroy. And Vasily Kivalona, she's a PhD student finishing and looking for a postdoc position. So if you're interested in excellent postdoc, let me know. All right. So so what is this problem about? So the first problem, well, both problems can be cast in a big family of problems that may be called network archaeology. So what's network archaeology? These are dynamically growing networks, and we've seen many of these in social networks or epidemiology. I don't have to talk too much about the importance of that. Rumor spreading computer networks. So when a network grows in time, and we observe this network when it's already very large, and we would like to know something about the past of this network. So we only observe a present-day snapshot of this network, and we would like to say something about the past. So these questions include: who is patient zero in an epidemiological context? Who started a rumor? The nodes in this network who are influential today have they always been influential, and so on and so on. Okay, so these are the type of questions that belong to this area of network archaeology. When observing a large networks that we know that has been growing, we would like to say things about what happened in the past. Okay. So in this talk, I'm only going to talk about very simple networks that are actually trees, and but often these networks are modeled as by very simple random growth dynamics. So here vertices arrive, let's say, one by one, and when a new vertex arrives to the network, then it chooses, according to some very simple rule, it chooses some vertex or vertices to attach to. Okay, so the simplest model is called the uniform attachment model. When the new vertex that arrives attaches to a randomly chosen vertex. Okay, so among all vertices that are already there, it chooses one uniformly at random and attaches to it. This is the uniform attachment model. And when the vertex only chooses one vertex to attach to, and we start with a single vertex, then this is going to be a tree. Okay, this is called the uniform random recursive tree that is grown like this. Okay, but often there can be other types of attachment rules. For example, in the famous preferential attachment model, when a vertex arrives, then it's more likely to attach to a vertex that already has many connections. Okay, so the probability of attaching, so the attachment is still random, but the probability of attaching is influenced by the degree of the vertices that are already in the network. Okay, so in the simplest preferential attachment model, that's called the linear preferential attachment model, the probability of attaching to a vertex is proportional to the degree of that vertex. Okay, so in this talk, these are the two models that I will consider: the uniform attachment and the preferential attachment models. And in the simplest case, when these are trees, okay, so when a new vertex arrives, it attaches to just one vertex. All right. So these are called as I already said, the uniform random recursive tree when the attachment is uniform. The preferential attachment model in the simplest linear case is when the probability of attaching is exactly proportional to the degree. This is a tree that actually has been around for a long time, and it's called a plane-oriented random recursive tree. For reasons I'm not going to explain, but there's a very simple way of a different way of describing these trees. Okay, and these have been, such trees have been very well understood in probability. Okay, so the first problem that I'm going to address is what we call the finding Adam problem. Okay, so so what we are shown is a large tree without the labels. Okay, so we know that vertex 1 arrives at time 1, vertex 2 attaches to vertex 1, then vertex 3 chooses a random vertex, attaches to it, and so on. So this tree grows like this, but now we erase the label. So all we observe is the combinatorial tree. Okay, but we would like to know, and this tree is very large, so imagine n to be huge. But what we would like to do is to find the root of the tree. So the root of the tree is vertex number 1. That's Adam. Okay. So the question is this possible? In what sense is it possible? Okay. So if I show you a huge tree that has been grown according to this these uniform or preferential attachment models, can we identify vertex number 1? Well, yes and well. No, the immediate answer is no, since vertex 1 and vertex 2, they are the same, right? They are completely equivalent, because at time 2, when vertex 2 arrives, then the tree is just these two vertices connected by an edge, and from that moment on, these two vertices are indistinguishable. Okay, so so in order to make this problem a little bit more meaningful, but we are allowed to select, when we want to identify the root, we are allowed to select not just one vertex, but a set of vertices. Okay, so we are allowed to select, let's say, k vertices. And what we would like to guarantee is that the root is in this set with high probability. Okay, with probability at least 99%. Okay, more generally, we are given a probability of error that we allow, that's epsilon, and now we are allowed to choose k vertices in any way from this tree, and we would like to guarantee that the root is among those k vertices with high probability. Okay, so the question is, how large does this k have to be? Okay, so clearly this depends on the probability of error and on the size of the tree. Okay, so large trees are expected to be more difficult, right? It's more difficult to find the root in a large tree, and if epsilon is very small, then the problem is also more difficult. So the question is, how large this k have to be such that we can guarantee that the root is in a set of k vertices that we can choose. Okay. Please interrupt me if anything is unclear. All right. So here's these are images that I chose that I stole from Igor Korchemsky. So this is what a uniform attachment tree looks like with 5,000 vertices. So this is what we are shown, and we would well, of course, this tree is drawn according to some kind of optimization algorithm that you see not all edges have the same length. So these are optimized for viewing pleasure. So maybe this is the root here in the middle, but who knows? We don't know that. So this maybe here is the root. Maybe this is the root. Okay. So the question is, how many vertices do I have to pick from this tree such that with high probability I can guarantee that vertex number 1 is among them? This is the same tree with 10,000 vertices, with 15,000 vertices, 50,000 vertices. So you see when the tree is big, so now where's the root? Finding Adam is now doesn't look that easy visually. Okay, all right. Preferential attachment trees look very different. Actually, this is known that they have much bigger hubs. So there are vertices that have much larger degrees. The maximum degree in a uniform attachment tree is about the logarithm of n, and here a maximum degree is about square root of n. So there are huge hubs in the preferential attachment trees. So the problem looks kind of different. Okay, so I'll talk about this. So let me summarize the results of this. So maybe surprisingly, the minimum number of vertices that I have to choose in order to guarantee that the root is among those k vertices with probability at least 1 minus epsilon doesn't depend on n. Okay, so finding the root in this tree, in this gigantic tree with 50,000 vertices, is not much harder. It's not harder. Well, it is a little bit harder, but not essentially harder than finding the root in a small tree like this. Okay, so it doesn't matter. And if you have 1 million nodes or 100 million nodes, the problem doesn't get harder. Okay, so that's one of the surprises, and this is true for in both models. So that means that this k only depends on epsilon, and the second kind of surprise that was surprising to us is that finding the root in a preferential attachment tree is actually harder than in a uniform attachment tree, even though you would expect maybe that in a preferential attachment tree, since there are these big hubs, the root should be a big hub like that, but it is not the case. It is provably easier to find the root in a uniform attachment tree, and by easier, what I mean is that this k of epsilon is smaller. Okay, as a function of epsilon, it's a smaller function than in the case of preferential attachment tree. Okay, so let's see how one can go about this kind of problem. So how do we find the root of such a gigantic tree? Well, the first idea that comes to mind is that old vertices are likely to have higher degree, right? Because they arrived at the beginning of time, so they had more time to grow. Okay, for example, in a uniform attachment tree, it's very easy to compute what the expected degree of the root is, right? Because at time 2, when the second vertex arrives, then the root has degree 1 with probability 1. And when the next vertex arrives, then it attaches to vertex number 1 with probability 1/2, at time 3 with probability 1/3, at time n with probability 1/n, right? So at time n, it's the harmonic number, right, which is about log base, the natural base log of n, right? That's the typical degree of the root, and you can easily prove a central limit theorem for this. This is just the sum of independent Bernoulli random variables. Okay. However, the maximum degree is much larger than this, and this is well known in about uniform attachment trees, that the maximum degree is log base 2 of n. Okay, so it's a constant times larger than the degree of the root. So if we choose the highest degree vertices, then if we only choose a constant number of them that doesn't depend on n, then we will miss, with high probability, we will miss the root. That's easy to see. Okay, so sorting by degrees is not gonna work. Okay, the preferential attachment model, this idea works a little bit better, but it's still far from being optimal. Okay, there, as I said, the maximum degree is of the order of square root of n, so it's a very different story. Okay, so what can we do if not sorting by degrees? Well, the idea is go by centrality. Okay, so this is a really simple method, and I will show you how it works. That chooses the most central vertices. So how do we define centrality of a tree? Well, there are various ways of doing this, and this notion is sometimes called the Jordan centrality of the tree, which simply for each vertex we can look at all these subtrees that hang off this vertex v. We can look at the size of the largest subtree. Okay. And a vertex is called central if the size of the largest subtree is as small as possible. Okay, so if a vertex is somehow in the bulk, in the middle of the tree, then all subtrees will be somehow smallish. Okay, whereas if you look at for example, if you look at a leaf here, then it has only one subtree hanging off it, and that has size n-1, so it's huge. Okay. But there's always a vertex such that the largest subtree is at most n-half. Okay, so that's our first root finding idea. Let's take the k vertices that are most central in this sense, right? So we just sort vertices according to the maximal subtree size, and we pick the k smallest of these guys. And now it's not difficult to prove, and I will show you the sketch in the next slide. That if k is about 1 over epsilon, well, it's 11 log 1 over epsilon, but the main order is 1 over epsilon. So if k is bigger than 1 over epsilon, then with probability at least 1 minus epsilon, we will hit we will hit the root. Okay, so the root will be among the most central vertices, the 1 over epsilon or 11 log 1 over epsilon most central vertices. Okay, so here's a really ugly slide about the proof. This is just a very simple sketch. So what do? we label the vertices chronologically. Okay, as we did so far. So vertex number 1 is labeled by 1, vertex number 2 is 2, and so on. And psi of I denotes this statistic that we work with. So this is the maximum subtree size of vertex I. Okay, so how can it be that the root is not among the k most central vertices? Okay, well, this will certainly happen if there exists a late coming vertex that is more central than the root. Okay, but if a late coming vertex is not more central than the root, this can happen by two different reasons. Either the root is not very central, or this late coming vertex is very central. Okay, so either so the probability that the root is not among the most central vertices can be upper bounded by the probability that the root is not central. And by not central, I just this is the right threshold. I could put any threshold here, 1 minus epsilon n, 1 minus epsilon n. This is the one that will give us the optimal balance. So this is the probability that the root is not has a subtree size which is very large, at least 1 minus epsilon times n size. Moreover, no vertex, there exists a late coming vertex that has no subtree size which is bigger than this. Okay, that is very central. Okay, so how do we bound the first vertex? Well, you see, this is vertex number 1 and this is vertex number 2. And let's put everything in one bag that attaches to vertex 1, including what attaches to its to the vertices to attach to 1, right? So these are all the subtrees that hang off 1, and the B is all the vertices in subtrees that hang off vertex 2, right? So we can partition the vertices in two ways. And you see these two bags behave like a polyarn, a very simple polyarn, where because when a new vertex arrives, right, then then it will attach to either A or to B, and the probability that attaches to A is just proportional to the number of vertices in A. So this is the simplest possible polyarn. Okay, and we know that the sizes of polyarns with this really simple replacement rule is uniform. Okay, so these two subtrees are uniform. So the probability that that the vertex 1 is has a subtree which is bigger than 1 minus n, that's smaller. Sorry, this psi 1 is definitely smaller than the larger of these two urns. But the larger of these two urns, well, these two urns are about uniformly distributed if we divide by n. So the probability that this is bigger than 1 minus epsilon times n is bounded by 2 epsilon. Okay, so this is how we bound the first term, and the second term is similarly a polyarn argument, because how can it happen that a late coming vertex I, which is not among the first k vertices, late coming vertex is very central? Well, if this is very central, that means that all these trees have a small size, right? Size less than 1 minus epsilon, because of, right? So, and that again, these bags behave as a polyarn, so we can just use the limit theory of polyarns and conclude that this probability is smaller than k times 1 minus epsilon to the k minus 1, and then if we optimize k, then we get that if k is about 1 over epsilon log 1 over epsilon, then the probability that the root is not among the k most central vertices is going to be smaller than epsilon. Okay, so that's a really simple rule, and and this analysis is actually sharp in the sense that that up to this logarithmic factor we cannot do better with this particular method, right? And the simple reason is that the root remains a leaf for after k steps with probability 1 over k. Okay, so so that means that after let's say 3k steps, the root is still a leaf with this probability. Okay, and that means that at that time the root is not going to be among the k most central vertices, and then it's easy to conclude that k has to be less than if bigger than 1 over epsilon. Okay, so so the question is, can we do better than 1 over epsilon for this k? Well, we can try to find the optimum rule. Okay, so what's the optimum rule? The optimum way of finding the root is the maximum likelihood. Okay, because for each vertex we can calculate what's the likelihood that that vertex is the root of the tree. Okay, so what does this mean? We can imagine for each vertex that that vertex is the root, and now we can count how many different ways the resulting tree could have been produced, right, by recursive labelings of the tree. Okay, And if we do that, then it turns out that the likelihood function is proportional to this expression. So let me explain what is this. So this TUV down arrow is the subtree of the tree rooted at U. So here we imagine that U is the root of the tree, and we look away from the root. And so this is vertex U, and this is vertex V. So we just look at this subtree size. Okay, the subtree of V when we look away from the root. Okay, so for each vertex, we take the product of these subtree sizes. Okay, and this and we have to worry about automorphisms, but let me just not even explain what that term is. Okay, so the point is that this is the maximum likelihood. Okay, so we know what the optimum rule is. The problem is that this is a complicated expression, so it's not very easy to analyze it. However, we can analyze it to get lower bounds. So I'm not going to go too much into the details, but with a very simple argument, we can prove that if k is smaller than something like e to the square root of log 1 over epsilon, this is much smaller than 1 over epsilon, then no method can work. Okay, so this is a lower bound that we have. Let me not go into the details. And we can also try to improve our upper bound that we got from the simple way of just finding the most central vertices by trying to analyze the maximum likelihood directly. We couldn't do that because of this annoying term that involves these automorphisms. So we just said, okay, so let's just pretend that it's not there, and let's try to minimize this function. Okay, so now instead of looking at just the subtrees that hang off a vertex, we look at for every vertex apart from this vertex U, we look at the subtree size that looks away from U, and we take the product of all those. Okay, so this is our new centrality measure. Okay, and we would like to minimize this. Okay, so this is a little bit more complicated than just looking at the sizes. And it turns out that this is better. This is strictly better than looking at Jordan centrality. What we could prove is that if k is larger than e to the log 1 over epsilon over log 1 over epsilon, then the k vertices that minimize this statistic, so the case most central vertices according to this measure will contain the root with probability 1 minus epsilon. Okay, and you see, because of the presence of this log 1 over epsilon in the denominator of the exponent, this is much better than any power of epsilon. Okay, so in particular, it's much better than 1 over epsilon that we had before. Okay.
So, Gabor, would you take a question now?
Of course, yes.
So there was a question earlier by Devavrat about commenting on both these algorithms, the complexity as a function of n, the size of the network.
This is maybe I skipped the slide where yes. So here, finding the most central vertices is really easy because this function is monotone along paths. So computation is really easy. It can be done in linear time. And this other one, that's a good question. The maximum likelihood that could be much harder. But yeah.
I also had a question. Now, you started with this application of finding the first patient.
Yeah.
Now, at least in India, we have a lot of missing data. So edges may be missing. Can you do something then?
These are wonderful questions. Yes, this whole area is kind of in its infancy. So there are many exciting questions, and yeah, I would love to hear nice models. So it's sometimes sometimes problems are immediately too hard. Sometimes they're immediately too easy. So it's interesting to find a nice model when you can kind of understand, for example, missing edges or missing missing data.
But,
Yeah.
from your analysis, wouldn't it be? It seems that if you just miss a few edges, since you're doing everything is based on sizes, it may not be that. You may be able to tolerate loss of a few edges. No.
Well, it's a tree, so if you lose an edge, then the graph disconnects. So yeah, I don't know how one can formulate this in the right way here. Yeah, I don't know what the missing edge means here. Maybe in other models when we don't have trees, then yes, then there should be some robustness. Here I don't know how one can deal with that. Yeah. Yeah, though maybe even in trees there's hope because somehow edges, yeah, if you don't have too many missing edges, that maybe you can argue that the bulk of the tree remains the same, maybe. But that's very interesting, actually.
Devavrat has one more question. You'll probably answer it. He's saying, is the conjecture that 1 by epsilon is the right answer? Is 1 by epsilon the right order?
Well, no, 1 over epsilon is not the best, because we can do better, right? We can do this. E to the log 1 over epsilon over log 1 over epsilon. And so I have a summary here on this slide. So there's still a big gap between the lower bound and the upper bound. I would guess that the upper bound is closer to the truth, simply because the lower bound is such a simple-minded argument. So I don't know. And what we do know is that what I mentioned earlier is that for uniform attachment, the problem, this k is strictly larger. It's much larger. It is between 1 over epsilon and 1 over epsilon fourth. We didn't really look for the optimum in this case. I would guess it's something around about 1 over epsilon, or maybe 1 over epsilon squared for preferential attachment. And the reason, let me just say one simple word about this. The reason why this is true, why preferential attachment networks are more difficult, is because if you look at what's the probability that the root is a leaf for a long time, then it's much larger. It's instead of 1 over k, it's 1 over square root of k. The probability that after k steps, the root is still a leaf. Okay, and the reason why this is because, so this is root number 1. This is vertex number 1, vertex number 2, and now if vertex number 3 attaches to vertex number 2, that has probability 50%, then the next vertex is now twice as likely to attach to vertex number 2 as the vertex number 1, and so on. Because of preferential attachment, if something goes wrong at the beginning, then it stays wrong for a long time. Okay, so it's much easier to miss the root. Okay, and we can prove. I'm not going to go in the details now. We can prove that in fact one cannot possibly hope for k better than 1 over epsilon. Okay, and this upper bound is again just a simple analysis of the Jordan centrality. So the same simple centrality measure that worked for uniform attachment also works here with the verse exponent. And the analysis is very similar, again, with a Pauli iron with a slightly different replacement rule. Okay, so this is this closes the first half of the talk. The second half is related, and I actually kind of need these results for the second half. But maybe if there are questions, this could be a good moment.
So is the lower bound here for the preferential also by taking the max likelihood? And is now would you say that that's closer to the truth?
So here, okay. So what is easy to see in the preferential attachment model is that it can happen with in a preferential attachment tree of size 1 over epsilon squared. The following can happen with high probability. Well, not high. It will happen with probability at least epsilon. is that the root is still a leaf, and vertex number 2 has about square root of n neighbors, okay, and that are also leaves. So there's no way of distinguishing the root from these guys, okay, and there are square root of sorry, there are 1 over epsilon of these, okay, if n is this of this size. Okay, so that's a very simple argument. We don't have to analyze the maximum likelihood. We can also write down what the maximum likelihood is. It's again, it's not too easy to analyze. Okay, so the second problem is the so-called broadcasting problem. That that is the following. So here, vertices have 2 colors, either red or blue. Okay, and the root has a random color that we don't know. Okay, and now when a new vertex attaches to so when we grow this tree, when the new vertex attaches to the parent, then it will take its color with probability 1 minus q, and take the opposite color with probability q. Okay, so think about q as a small number here, even though later I will discuss the case when q is big, but think about q as something small. Okay, so in a typical case, when a new vertex attaches to an existing vertex, then it will take the same color with high probability, but with some small probability, it's a rebellious child and it changes color. Okay. And now what we observe is an unlabeled tree, so we don't see the labels 1, 2, 3, n. It's an unlabeled tree of size n, and all we see is the colors of the vertices. Okay, so we see this red and blue vertices, and we would like to guess the color of the root. Okay, so the question is, what's the optimal probability of errors? This is a classification problem, and we would like to guess what's the color of the root. Okay, we don't know what the root vertex is. What we see is this. Okay, so sorry, so this is the tree that we generate. This is the root number 1. It's blue in this case. Then root number 2, when it attaches, it takes the same color. Vertex number 3 it takes the same color. Vertex number 4, I can't find it. It's here. Vertex number 4 was attached to 2, but it was a rebellious child. It changed its color. Okay. Vertex number 5 was not rebellious. It attached to here, and so on and so on. Okay. Vertex number 6 attached to 1, and again it was rebellious. Okay, so and so on. This is how the tree is grown. But now what we observe is this tree. We don't see, of course, these labels. So I show you this tree with the colors of the vertices, and the question is, what is the color of the root? Of course, we don't know where the root is, but can we guess the color of the root? All right, and what's the smallest probability of error that we can get? This is the classification problem. There's a more difficult variant, and this is called resembles more to the classical broadcasting problem on trees, is when we only observe what happens on the leaves of the tree. Okay, so it's the same. The tree is grown exactly the same way as before, but what we observe now is this. So we only observe the unlabeled tree, and we observe the colors of the vertices. And the question is, can we guess what's the probability? What's the color of the root? And what is the smallest probability of error that we can achieve? Okay. And in the rest of the talk, I will only consider the uniform attachment model, though we also analyze the preferential attachment model, and actually the results are quite similar. Okay. So the first obvious observation is that the smallest probability of error is at least q over 2. Okay, so why is that true? Because with probability q, vertex number 1 and with probability q, vertex number 2 is a rebellious child, and they change its color. So at time 2, with probability q, what we have is a red and the blue vertex, and from then on, these two are completely undistinguishable, and anything can happen. So on this event, we make an error with probability 1/2, no matter what. Okay, so the optimal probability of error cannot be smaller than q half. This is completely trivial. Okay. Well, what's the optimal classifier? Well, we can determine the optimal classifier because we know for each vertex we can compute the likelihood of that vertex is the root. Remember that we had this ugly big expression. So this psi sub t of u, this is the likelihood that vertex u is the root. So what we can do is that we can add these up for all blue vertices and add up the likelihoods for all red vertices and compare them. And this is the optimal classifier. Okay, but of course this is difficult to analyze. So what we will look for now are simple classifiers, and we will see if we can what we can say about them. All right. So, of course, the first idea, especially after the first half of the talk, is that we can use root finding algorithms, right? So if we can identify the root, then of course we know the color of the root. Well, we could not really do that, right? What we could do is that we could find k epsilon vertices that contains the root with high probability. So we can just look at that subtree and take let's say the majority of the vertices. Okay, so take any root finding algorithm that finds k of epsilon vertices. Look at the colors. We know that with high probability the root is among them, and take the majority vote among those. Now it's very easy to analyze this, right? Because we have with probability epsilon, we missed the root. The root is not among these guys, and if all the other vertices have the same color, then of course we're gonna be correct, right? If it's not, then it's an upper bound for the probability of error. It's actually not a bad upper bound, even though it looks very crude, but it's not a bad upper bound. So what we get is that the probability of error of such a method is at most epsilon plus q times the optimum value of k epsilon. Okay? So if we plug this back to what we had, then for the uniform attachment model, we get that the probability of error is at most q to the 1 over log q. And for the preferential attachment model, we get something much worse. All right. So this is quite interesting. Of course, now it's not that surprising that these probabilities don't depend on the size of the tree anymore, right? Because we can kind of identify the root irrespective of the size of the tree. And you see in the uniform attachment case, we are quite close to the lower bound, to that silly lower bound that was here, q half. Okay, we get if q is very small, then this 1 over log q is sorry, there I guess there should be right. Then this is very close to linear, but it's not quite. Okay, so the question is, can we do better, right? So this is simply just plugging in the root finding algorithms. And this analysis cannot be improved. That's easy to see. However, when we would like to only guess the color of the root and not finding the root, right? Well, now we don't really care about finding the root. All we want is to find the color of the root. It makes more sense not to try to zoom in and find a small subset of the vertices that contain the root, but try to find vertices that are close to the root with high probability, right? Because if we know that a vertex is very close to the root, then with high probability it will have the same color as the root. Okay, so in particular, if we choose using some method, if we choose a vertex v, and capital D is this is a random variable, of course, it depends on our method. If D is the distance in the graph distance of this vertex to the root, then it's very easy to see that the probability that the chosen color, and we just look at the color of this vertex, then you see this method will make a mistake only if if there's an odd number of times when on the path between the root and this vertex v, the number of color changes is odd, right? And the probability of that is bounded by q times the expected distance. Okay, so if we could find a vertex whose expected distance is a constant from the root, then we would get a method of guessing the root that has a probability of error proportional to q, which is the best one can do. Okay, and it turns out that this is actually very easy, right? Because what we can do is simply choose the vertex, the most central vertex, according to the Jordan centrality. Right? Remember, this Jordan centrality is just the vertex that minimizes the maximum subtree size. Okay, so let's take that central vertex. Then in both the uniform and the preferential attachment model, we can prove that the root is within distance log 1 over epsilon to v star, independently of n. Okay, so in other words, the distance of the uniform, the distance of the most central node from the root is bounded by an exponential random variable. Okay, and in particular, we can prove that the expected distance is bounded by is less than 5. Okay, so it's typically very close. All right. So, and the proof is again just a very simple Polyarn argument, because for a vertex, let's suppose that there's a vertex VT here, okay, that is such that this path has length t. Okay. Now you see, how can this vertex be more central than the root? Well, it must, if this is if this vertex is the centroid, is the most central vertex, then it must be that here in this subtree that looks away from the root has more than half of the vertices. Okay, but now we have this urn model where in urn number 1 we have these t minus 1 vertices, and urn number 2 we have 1 vertex at time t. And now the probability that this will happen is bounded by is exponentially small. It's something like 2 to the minus t. Okay, so so this is a very simple Polyarn argument, proves that the distance of the most central vertex to the root must be bounded by an exponential random variable, meaning that the probability that that this distance is bigger than c times some constant times log 1 over epsilon is less than epsilon. Okay, and if you work out the numbers, then we get that the expected distance is at most 9 halves. All right. So so what we get, and we get this for both in the uniform and preferential attachment models, that the optimal probability of error is now is linear, is between q half and q. So when q is very small, then this silly lower bound is actually very close to the optimal. Okay, so what makes guessing the root, the color of the root, difficult is at the very beginning there's a color change that happens with probability q. Okay, and moreover, with the same method we can also prove that whenever q is smaller than 1/2, right, meaning that remember q is the probability that a newly arrived vertex takes the same color as the parent, is smaller than 1/2. So whenever it's smaller than 1/2, then we do strictly better than random guessing. Okay, I ran out of time, so I'm gonna just very quickly wrap up. Let me just mention that in the more difficult model, when only the leaf colors are observed, the same holds. The same inequalities are still true, and the reason is that we can prove that there is always a leaf very close to the centroid. Okay, so what we can do is that choose the centroid that will not be a leaf with very high probability, but with very high probability there will be a leaf which is very close to it at most constant distance, and then our arguments work. And yeah, maybe in 10 seconds, another very simple method is just counting how many red and blue vertices are there in this big tree. Okay, and it turns out that this works if Q is not too large. So in the uniform attachment model, this method will break down when Q is 1/4. Okay, so when the probability of a rebellious vertex is bigger than 1/4, then taking the majority doesn't work anymore. But before that, it does, meaning that the probability of error of a simple majority is going to be strictly better than 1/2, and moreover, it is linear. It is linear in the in Q for small values of Q. Okay, and let me finish by giving you these two references. So the first half of the talk was about this finding Adam problem. It's a 2017 paper, and this broadcasting paper is much newer. Okay, thank you.
Thank you. There are a couple of questions. I'll just let the participant just kind of unmute and ask the question. So,
of course.
Sina, if you want to go ahead, and then maybe Devavrat after that.
Yeah, thank you. Hello. So
yes.
Thank you very much. And there was this variant of the model where only some of the nodes were observable. The last one that you discussed. So
yes.
Yeah, I'm not quite sure if all the information regarding the hidden ones are missed or just the colors.
So what we observe is no, just the colors. So this is what we observe. Okay, we observe the combinatorial tree with the leaves colored.
Thank you very much.
Okay, so in particular, what we can do is that we can find the centroid of this tree, right? Let's say it's this, and now look at a closest leaf, and take the color of that, and that will work.
Right.
So my question was just I seem to recall that there was some work by Elkanan, Mossel, and Yuval Perez on propagating the labels from the leaf up to the root.
Right.
So your results should be better than theirs, I assume.
No, these are not really comparable, but yes. So they call this the broadcasting problem, but they typically consider, let's say, the simplest model is you take a complete binary tree, and now the root has a color. It's the same kind of propagation, and then you look at what happens at the leaves. Okay, and now they try to see up to what time, so how deeply can we go, such that there's still information about this, the root value can still be guessed. What we do is that we look at the same model for these recursive trees. Okay? Instead they look at Galton-Watson trees or this complete binary tree and the trees of that kind. Our trees are recursive trees that are very different, right? In particular, in our trees, there will be always leaves close to the root, and that's what makes it easier. Okay, because in their case, of course, all the leaves, all the information is far from the root, and then there are interesting phase transitions that happen. Okay, so, but it's the same problem, just on different kinds of trees.
Thanks.
So any more questions?
Hello. It was a nice talk. Actually, my question was, you're saying that K doesn't depend upon N, right?
Yes.
But in the proof, it appears like you are taking the asymptotic analysis of the urn-based models, right? So
Yes.
in some sense, that's the reason why it is not depending on N. Am I?
No, of course it's a lie. I'm not saying that it's yes, it is, of course. So of course it does depend on N, but it doesn't get harder with n. Okay, so the problem, so of course the problem becomes harder and harder and harder, right? If n is larger in both finding the root or guessing the color of the root becomes more difficult, but in both cases, in the first case, the number of vertices that we have to choose can be chosen independently of n, and that will work for all n. Okay, so of course the problem becomes harder, but not much harder. Okay, so that's I should have said it like that.
Okay.
Okay.
Thanks.
Yeah.
Okay, so there are no more questions. Thank you, Gabor. That was a very nice talk. Thank you very much.
Thank you.
On behalf of everyone. We have now, I guess, 3-4 minutes to get coffee and do other things that we do. So we'll start in another 3-4 minutes. Let's just say by 6:31 Indian Standard Time. Thank you.
So Piyush, do you hear me? Am I audible?
Yes, you can.
Yes, sir, it's audible.
Yes, we start in a couple of minutes.
Yeah. So, shall I start sharing my screen or?
Yeah, you can. Yeah.
Sir, please share your screen.
Okay. So, I hope you see.
Yes.
But,
You can make it full screen.
yeah. So,
Yes, sir, it's visible.
right.
Sir, can you forward the slides?
Sure. So do I have just ready it now?
Yeah.
Up to the top. Okay.
Yeah. Oh.
So can I do it after the talk? Is it possible? Or
Okay, sir. Sure.
no, thanks.
And for the questions, so we usually like have everyone putting them in the chat box, and then once in a while, so maybe you can stop it whenever you think you can take some questions. And
Yeah, sure. Well, I think that's good. I don't mind.
Sir, if you're okay with recording the session.
Yeah.
Because we are doing the live streaming also.
Yeah. Okay. Sure.
Thank you, sir.
okay, so maybe we can start now. Okay, so so we're very pleased to have our next speaker, who is Shubhajit Goswami. So he's a faculty member in the mathematics department at TIFR and also an associate faculty member at ICTS. So he has worked on linear quantum gravity, on Gaussian free fields, percolation. But today he'll be telling us about some problems about fitting piecewise polynomial functions to data. He before coming to TFR, he was at IHES as a postdoc and at the University of Chicago for his PhD. So with that, over to you.
Okay. Thank you, Piyush, and good evening and good morning to everybody. I thank the organizers for giving me the opportunity to talk about this work, because I think, as Piyush told, I mostly work on moments in probability theory, but another work of my work that gets often I don't get much opportunity to talk about theoretical statistics. So thanks for that. Okay, so today the title of my today's talk is Adaptive Estimation via Optimal Decision Trees, and it's based on a recent work with Sabyasachi Chatterjee, who's in the Department of Statistics in UIUC. So the primary motivation behind this work of ours came from this actually quite famous paper by David Donohoe, published in Annals of Statistics back in 1997. It's called Curved and Best Orthonormal Basis Connection. So what he does here, he introduces a methodology called the dyadic curve as a non-parametric regression method for estimating two-dimensional signals. So the card here, as usual, refers to classification and regression tree. But how is it different from CURT? Regular CURT is that, while CURT, you generally compute a locally optimal decision tree, make the locally optimal partitions each state. For dyadic CURT, it computes a globally optimal dyadic decision tree, okay, based on solving a penalized least square optimization problem. And then what Donohoe shows in this paper that this estimator is minimax rate optimal of the class of bivariate functions which show anisotropic smoothness. So if you think of it as like modulus of continuity, it follows different. So you can see it, catch a glimpse of it here. So it has like different ordered exponent in different directions. Now, of course, you have to compute a globally optimal dyadic decision tree, but it turns out that in this case, it's actually easy computational. You can compute it in linear times in the sample size. So then, and we're working on I and my co-author, we're working on some other methodologies and for estimating some non-parametric function classes. And then it occurred to us that it might be actually this idea and some extension thereof can be useful in actually estimating the class of functions that we're interested in, and some of which I list here. The first one, and probably I'll mostly spend today's talk on that one, is the functions that are piecewise constant or piecewise polynomials with fewer pieces in general dimensions. Then there's a class of function, or essentially it's probably most popular in 2-dimension, where the class of function consists of images or matrices that have bounded variation. And a popular method for estimating this class of functions is so-called total variation denoising, or TV denoising. Then there's a class of in dimension 1, the functions whose some higher order derivative. Okay, so for example, for total variation is just, you can think of it like first order derivative is well, the function is bounded variation, and well, you can actually require the higher order derivative to have bounded variation instead of just the function itself, which requires some kind of integrability of the bound on the integral of some higher order absolute derivative. And popular methodology for estimating this class of functions is the so-called trend filtering. And what turned out from our work is that not only does dyadic curve offer similar, risk bounds as these methods, they actually sometimes offer better risk bounds, and at the same time are computationally fast. And so, hopefully in the course of the talk, I'll be able to convince you of some of these merits. So for simplicity of exposition, I'll mostly focus on the class of functions that are constant on fewer rectangular pieces, but I hope to be able to give you enough hints and some slides to convince you that how actually the similar estimates give you good bounds and for the other classes of functions I mentioned here. Okay, so let's start with this, the piecewise constant signals. And let me first describe the setup. This is the usual setup for non-parametric regression in fixed design. So, well, our signal will be a d-dimensional array. So it's a function indexed by the d-dimensional grid of side length n. And what we observe is that the signal with the noise, sigma is the noise strength, and the entries of the noise array are mean 0 and independent sub-Gaussian random variables. Okay, and well, we measure the performance of an estimator by the usual mean squared error. That's average the squared loss, expected squared loss over the sample size. So capital N is little n to the power d, which is the sample size. Okay, and this norm is the usual Euclidean norm. Okay, so that's a very standard setup. And how to define piecewise constant? Let's be precise. Although this is probably quite obvious. So we define a rectangle to be, as you can expect, it's the product of disjoint not disjoint actually shouldn't be there, d-discrete intervals. And rectangular partition of such a rectangle, simply a collection of rectangular subsets of this rectangle whose union equals the whole set. And we call an array indexed by the d-dimensional grid to be piecewise constant if there exists a rectangular partition such that this array restricted to each such rectangle, which I'll henceforth refer to as the blocks of the partition, is constant. Okay. So defined is this way. Well, every array is piecewise constant, right? Because every vertex in the d-dimensional grid is a rectangle. So that's why it makes sense to introduce this functional called KL theta star, which is essentially the cardinality of the coarsest rectangular partition that you can define such that theta star is constant on the blocks of pi. Okay, that's the natural definition. And we call theta star to be piecewise constant with k pieces if the scale theta star equals k. So that's it. Okay, if you have any question about the setup, just let me know. Okay, so now how to estimate such class of functions? Well, if somebody told you, let's say your oracle, that exactly the partition, so exactly what the blocks are, then, well, you'll just do the trivial thing. You'll just go to each of this block and feed the average, okay? Because that would be the least square estimate. And this will give you, like, standard, as we all know, like using the standard methodologies, that this estimate will incur sigma squared times scale theta star over n as an MSE. Okay, but of course we don't know that. And then using, actually, this is not far from the minimax rate for this class. Actually, using information theoretic arguments, you can show that the minimax rate for this class of functions is actually this, what you see here, sigma squared times k over n times a log factor. Okay, actually, this follows from the same result for signals that are k sparse, actually. So because the signals that are k sparse, you can easily show that it's contained in the class of signals that have at most, let's say, some constant times k pieces, and hence it follows. Okay. So now, what is our objective? We intend to obtain an estimator in all dimensions that satisfies these two properties. The first, it attains this minimax rate Riggs bound, or sigma square k all over n times log n, adaptively for theta star. What I mean by adaptive is that, well, okay, you do not focus know the true partition or what is the cardinality of this course's partition, but it risk will automatically affect, automatically reflect, automatically attain this the minimax rate for the class of signals of that number of pieces. And second, it should be computable. Of course, you can go around and search over all possible partitions, but that's not very practical. We want to be able to compute it in volume time, at least in the sample size. Now, before this work,
so here the oracle, so the block partition is not known.
No. So nothing is known. Yeah, you don't know k, you don't know the partition, nothing. Yeah, you just have that. So before this work, these types of problem, well, similar flavor have been studied with other estimators based on convex optimization. So one of them is as I told you, and I'll actually talk a bit probably in the course of the talk, is called total variation denoising, and that we and my co-author studied in a different paper. And there is a slight variation of that called Hardy-Cross variation denoising, which is essentially a bit tweaking the definition in the discrete setup. That was studied by Ortelian van der Kier in 2019 and Fang, Guntergoina, and Sein in 2020. And none of them actually we could, in our paper, we proved that, you cannot obtain better. So the rate was like k to the power 3 over 4, sorry, k to the power some power, like bigger than 1 over n to the power 3 over 4. Okay, and we proved that you cannot do better than that. Here, actually, Ortelian and van der Kier achieved 1 over n rate, but the dependence on k is suboptimal, was actually, as far as I know. So far, to the best of our knowledge, before our work, these questions have not been rigorously answered in the literature, in the machine learning or statistics literature. And so, I hope to be able to propose a solution in the course of this talk.
Okay. The question, so do you learn the partition as well?
Sorry.
There's a question from Sandeep, which is, do you learn the partition as well? Like, so do you just learn?
Yeah, I learn the partition as well. Yes. Yeah. But okay, we don't put a metric on that. Our loss function doesn't reflect that, but I'll describe the estimator shortly. Yeah. Any other? Okay. So let me now define dyadic curve. Okay. And let me define it and I'll then state the main results. So in order to do that, let me define how we call here the dyadic, recursive dyadic partition. So let me define a move called dyadic split. So take a rectangle. So I have drawn a doodle here with my inefficient hand. Hopefully this does, because I don't have an iPad, unfortunately. So a dyadic split of a rectangle is simply you choose one of its d sides and you just split it into half. Okay. And then you take one of the rectangles obtained and apply the same, apply the same split. Okay. And you go on iteratively recursively with this procedure. Okay. So generating finite and finite partitions, and all the partitions that you can get using such splits in an iterative fashion will be called a recursive dyadic partition. Okay, so that's the definition. For example, here, so this procedure, this is a recursive dyadic partition. Okay. Just for convenience, I'll denote the set of all recursive dyadic partitions of the d-dimensional grid to be calligraphic PRDPDN, or since the D and N will be mostly fixed throughout the top, simply denote them as calligraphic PRDP. Now consider the following minimal partitioning optimization problem. So what you do is that you just take the squared loss penalized by the cardinality of the partition times the tuning parameter lambda, non-negative tuning parameter lambda, and you look at the partition which minimizes that. Okay, so of course I have to explain to you the meaning of pi y, but probably you have already guessed, is essentially the orthogonal projection of the observation matrix or vector, if you see them as an element of Rn, onto the subspace of matrices that are constant on the blocks of this partition pi. Or more simply, even simpler words, it's just the matrix that you obtain by assigning to every block of pi the average value of y over that block. Okay, it's simply that. Now let me just take this opportunity to describe like how we adapt it for piecewise polynomial. So there, essentially you have a family of functions. In this case here, just constant function, just one. In that case, we do have different bases like polynomials of degree at most r, right? You have some basis functions, and you will just regress in each block. You will just regress on these functions, okay, into a linear combination of these functions. That's what you will do. That's the immediate way to generalize this. Okay, so it just works verbatim. And so that's the optimal partition, pi hat RDP lambda, and the estimator is essentially the observation vector averaged over each blocks of this optimal partition. Okay, so this produces a piecewise constant array on the partition pi hat optimal partition. Okay, of course, you minimize it over the class of recursive dyadic partitions. And this is precisely the dyadic curve estimator I was talking about that was proposed by Donovo in dimension 2. Okay, is the definition clear to everyone? Okay. Anyways, and I'll probably take some time later to argue, to explain to you, but let me just state it here. This optimization problem, you can solve that at most linear basic operations by dynamic programming. Okay, it's quite easy actually to show that. Okay, so that's your estimator, the definition. Now let's come to the risk bound. So for that, in order to phrase that, I have to define this side alteration of the functional k all theta, right, that I defined for you earlier. So it's a similar thing as, again, the cardinality of the minimal partition, the number of blocks in the minimal partition, so that theta is constant on the blocks of pi, except that now you do this minimization over the class of recursive dyadic partitions. Okay. So evidently, since it's more a constraint, it's it's clear that this KRDP theta is bigger than K all theta. Okay, and we'll come to that issue, but let's keep that in mind. So with that definition, Now, let me state the Ritz bound, which is the Oracle Ritz bound for dyadic Kurt. So if you choose tuning parameter to be like absolute constant, which you can precisely estimate, times sigma square times log n, then the following holds that MSE is bounded by what we can see here. I think I don't read that, but let me help you to interpret this. So suppose, forget that KRDB theta is actually bigger than KL theta. So let's say theta star, your true signal, has is a constant on the blocks of a dyadic partition with k blocks. Okay, let's assume that. So it's not only just any partition, the pieces they also form a recursive dyadic partition. Then you just plug theta equals theta star here. There is an infimum in this bound. This disappears. So what you get actually is lambda times the number of pieces over n. Okay, so that really looks like what we're aiming for, except that the true signal has to be constant on the blocks of a recursive dyadic partition instead of any partition. Right. So okay. So where do we stand now? Now let me try to address the issue that KRDB theta can be big compared to KL theta. Okay. So how big can that be? How big can KRDB theta be compared to KL theta? It turns out, and actually it's not particularly difficult, it's a simple combinatorial exercise. In dimensions 1 and 2, you can refine any partition, okay? You can refine any partition into a recursive dyadic partition by increasing the number of blocks by a polylogarithmic factor, okay? So C log n to the power t. So what this means in the context of the theoretical bound that I just presented to you is that under our choice of lambda, in dimensions 1 and 2, this estimate, recursive dyadic curve, attains the rate we're aiming for, except that except at the cost of a polylogarithmic factor, log n to the power t. Okay, the true rate will be log n. Okay. Okay, so we're quite close, but and it's computation efficient, so that's not bad. But still, it would be good, of course, to get the true rate, like to attain the minimax optimality rate, optimal minimax rate. And of course, we would like to do it for all dimensions, at least for low or moderate dimensions. So to fix that, let me present a slight extension, slight modification of this estimator, which we call optimal regression tree. So what we'll do here is that we'll extend the class of partitions from recursive dyadic partitions to what we call here hierarchical partitions. So let me define that for you. And again, there is a doodle if that's helpful at all. So what you do here, again, so there is a move, it's called hierarchical split, where you take a rectangle, unlike before, except, and you choose one of its sides, let's say this one. Now, contrary to the dyadic partition, here actually you can choose the partition, you can choose it to split along any point. Okay, so it's one of the endpoints, little endpoints, instead of just the middle point. Okay, so the split produces two rectangles, which may not be of equal size. Okay, and then you just repeat the procedure with the rectangles that you so obtain. Okay, and keep on generating finite and finite partitions, and any partition that you can obtain by a sequence of such moves, you call a hierarchical partition. And so, hierarchical partition, essentially, if you think about it, it parallels the evolution of a decision tree. Okay, that's essentially a decision tree. If you think of it as a set space of predictive variables, you're splitting your space in every step into two parts and trying to get at some partition. So that's what you're doing. Okay, so that's hierarchical partitions. Hopefully that definition is clear. Again, of course, it's still better than, it's still more general than recursive dyadic partitions, but still not all of them. doesn't cover all the partitions. So here are some 3 pictures I put up. I don't know how helpful they'd be. The first one, okay, I'll just leave you to verify for yourself. It's a recursive dyadic partition. The second one is a hierarchical partition, but not a recursive, not a dyadic one. Actually, you can confirm that by using that split. But what is more clear actually is that this partition is a partition, of course, but it's a rectangular partition, but it's not hierarchical. And that's easy to see because from the definition, you've got to have at least one split that spans left to right or top to bottom, which you don't see here, okay? Again, but well, we probably don't care that much about whether every partition is a hierarchical partition as long as it admits of a refinement into a hierarchical partition without incurring too much in terms of the number of blocks. And I'll come to that shortly. But before that, let me define the estimator, and it's just similar, except that you extend the class. So again, let's call calligraphic P3 to be the class of the set of all hierarchical partitions of the grid. And then we define the estimator in a similar way to be the partition optimizing this penalized least square, penalized square. But now you look for the minimum in the class of all decision trees, okay, or all hierarchical partitions. And you define the corresponding estimator. That's what we call the optimal regression tree estimator, ORT estimator. Again, so what is the computational complexity? And I'll explain to you that after a while. Well, of course, you incur a bit more cost, but not too much. It's in the sample size is square 2 plus 1 over t basic operations. So it's still not too bad. It's quite good actually. Okay. And yeah, again, this generalizes very naturally if you wanted to fit piecewise polynomials instead of piecewise constant. Okay. Now let me present the analogous Briggs bound. It's almost similar, except now your functional, this k theta is now k3 theta, which is a similar thing, the minimum number of blocks in the partition in which your theta is piecewise constant, blockwise constant, except that now the minimum is over all hierarchical partitions. Okay. So since hierarchical partitions contain recursive dyadic partitions, you definitely have that. This k3 theta is sandwiched between these two, k all theta and krdp theta. And you have a similar bound, just like before, except that krdp theta being replaced by k3 theta. Okay, so very fine. But now how does it solve the problem that it was designed to address, right? Because we wanted to address the discrepancy between krdp theta and k all theta. Let's see how does this one fare in that regard. Here, we are a bit luckier. And here, let me invoke some results from computational geometry from early 90s and early 2000s. So what happens that, well, in dimension 1, first of all, although in dimension 1 has been done before, so but just let me say it, any dimension is a hierarchical partition. So the problem is really there for high dimensions. Okay. In dimension 2, this is a result by Barman and co-authors from 2002, which says that any partition admits of in dimension 2 admits of a refinement into a hierarchical partition, whereas number of blocks increases by a factor of at most 2. Okay, so that means, in view of the result in the previous slide, at least for d equals 2 and of course for d equals 1, for our choice of lambda, we get this rate that we were aiming for. Okay, so as things stand now, we have achieved using this VRT both objectives, because it's also computable. Okay, I have to prove that, I have to probably convince you, but if you believe me, it's also efficiently computable in a sense, and it attains the minimax rate adaptively. Okay, so for d equals to 2, we have achieved our goals with the single estimator. What about other dimensions, higher and moderate dimensions? There actually, it's a bit we need to assume a bit more, but still not too much. So what you have to assume is that the partition is regular enough. The blocks of the partition are not too thin, which means that the aspect ratio, which is simply the ratio of the maximum side length over the minimum side length, is not too big. They're not too big. So we call a rectangular partition to be alpha fat, where alpha is a parameter bigger than or equal to 1, to be alpha fat if all its blocks have aspect ratio bounded by alpha. Okay, so that's a reasonable assumption, not too bad. Now, if you grant me that, then there's a result by Borkar from 1995. It says that for any alpha fat partition in any dimension, it admits of a refinement into a hierarchical partition whose number of blocks increases by a factor which depends most on the dimension and of course on alpha. Okay, so if the rectangular level sets of your true signal are all alpha fat, okay, which is not a bad assumptions to make, I guess, then it is indeed true that we also attain in all dimensions the minimax rate. Okay, our estimators also, we are able to obtain both our objectives. Okay, if you have any questions, I can stop, but let me take some time to summarize our main results before I go to computation and a bit about other things. So what we have is that the dyadic curve attains the respawn k all over n times polylog in log n for all theta star in dimensions 1 and 2. Then optimal regression tree actually attains the minimax rate in dimensions 2 and of course in 1. It continues to attain this this improved respawn in higher dimensions as long as your true signal is regular enough, like it's all level sets are fat, and the dyadic curve is computable in linear time, whereas ORT is computable in n to the power 2 plus 1 over t times many basic operations. Okay, so that's actually what we have gotten so far. Okay, so let me now tell you why actually these very briefly try to argue to you why it attains this rates of the complexities I mentioned. So, and it's basically because of the nature of the additive nature of the objective function, which allows for a divide and conquer principle. So let me define for any rectangle R, okay, a version of this problem restricted to R, which is simply you define the same problem, except that now you are looking at the partitions of the rectangle and the vector, the observation array restricted to R. Then it's quite easy to see from the nature of the objective function that your problem R can be computed in this way. So from you take the optimum minimum over all non-trivial splits of the rectangle, and you compute the value of the problems for each of the separate rectangles, and you obtain the one for which it's minimum. Okay, that's it. So what it means is that if we have this, if we can compute the value of the problem for each rectangle R, then of course I can go top down and compute the optimal regression, the optimal partition, and as well as the value of the estimator very easily. And how do you compute that? This rectangle for each one, okay, and that you do in a bottom-up fashion. So okay, you start from rectangles of size 1, okay, and then you move up in terms of the size of the rectangles, okay. And what you do, well, once let's say for a given rectangle where you want to compute the optimal split as well as the value of the problem, you already know that the value of the problem for rectangles of lower orders. So you can essentially, what you have to do, you have to actually do a comparison involving all the such possible partitions, all such possible splits, then let me remind you how many are there. Well, for each side, let's say I'm talking about optimal regression tree, okay, the hierarchical partitions. Well, in each side, you just do at most little n many. So there are d sides, so little n times d many. So that's why these terms come from, okay? That's all, okay? And you have to do that for every rectangle. And how many rectangles are there? Well, that's very easy to compute. That just capital N squared, right? Because essentially you have to obtain an interval in each dimensions, and the number of intervals in each side is at most little n squared. So you take to the power of d, you get capital N squared. Okay, so that gives you this capital N squared times little n. So recalling the little n is essentially capital N to the power 1 over d, you get the rate I just described. Okay, and why is it better? Why is it better for dyadic curve? And the thing is that there, the number of comparisons at each step is actually of order of constant, right? Because they're actually, the split is dyadic. So essentially given a side, there is exactly one split. So there are a constant number of splits. So this goes away. And there also you are constrained to only dyadic rectangles. And you can convince, and it's a very easy argument to prove that the number of dyadic rectangles, some rectangles of d-dimensional lattice of sign like little n, is essentially order of capital N. Okay, so that gives you linear order. So that explains how actually you'd compute these estimators. Hopefully I was a bit too fast, but hopefully I could convince you. Okay, now let me take some time to explain at least how this results, how these estimators also continue to perform well for at least one other interesting class of functions, namely that of bounded variation functions in 2D. Although in our paper, we consider more general classes in all dimensions and more general type of functions. But let me focus into that. So let us recall, or probably, what does the class consist of? So we define the total variation for two-dimensional metrics to be essentially the sum of the differences of the matrix along all the edges of the grid, normalized by little n. And this normalization is done so that if you imagine this theta u's to be relation, of a smooth function on the unit square on a regular grid of separation 1 over n, then this is exactly what we need to do, that is exactly what you need to, how you need to normalize it so that it gets comparable to the total variation of that function as a smooth function of the unit square. Okay, that's what it is. I think also that, so you'd expect that to be constant for bounded variation functions. Okay. And a very popular estimator, as I hinted earlier in the talk, for estimating this class of functions, is the so-called total variation denoising estimator, which is first introduced in the context of image denoising, of course. And it was in a very famous paper by Rhode in 1992. So what does the estimator do? Is that it you consider the penalized, the penalized estimator where the penalty term consists of the total variation of theta, okay, multiplied by tuning parameter. That's what you do. And a form of this estimator, that's what we consider in our earlier paper. And as I told you, this doesn't seem to attain the objectives that we laid out for us for this work. Okay. Now, what about this class is that, okay, but however, this TVD denoising estimator, although it doesn't add up nicely, it does attain the minimax rate, so the minimax rate for the class of functions whose total variation is bounded by, say, some number capital V. And this was shown in these works by Hunter-Rigole, 2016, and then Sadhanala and his co-authors in the same year. And that's essentially, the rate is V over square root of n up to log factor. And actually, well, probably I'll be able to convince you why the rate comes I think using our estimator. But anyways, okay, so this is the minimax rate up to polynomial factor. And here is our result for dyadic card. We just apply the same, so there's no problem, right? Because the estimator doesn't assume anything about the number of pieces or anything of that sort. So if you use the estimator to estimate for this class, you attain this rate, actually. Okay. So let me try to convince you how actually you get it briefly. So let us just recall, here I just recall the bound that we get for dyadic card. Okay, so that's actually the bound. Okay, so now what we will do, unlike in the case where theta star has a few pieces like k pieces, now I will not do that. Now we will really take advantage of this infimum. So what we will do is that, well, we'll use the fact the total variation of theta star is bounded by v star to be able to obtain some kind of approximation, of it in terms of a matrix theta that has quite a few number of pieces. Okay, so I'll approximate it by a matrix, it's a piecewise constant matrix with a few, depending on, of course, v, the parameter, few number of pieces. Then I'll just approximate it by that. So what I'll incur is that two parts. One part would be the number of pieces here of that matrix with which I approximate, and then the approximation. And both of them actually for this matrix would be of the order of like, essentially v times, okay, v over n, if you define v a different way, but v over square root of n. Okay. Both of these will give you the same term, which actually is similar to this. Okay, so I'll just not go to any details, but let me just tell you what we do is that here is how it looks like. So what you do, you take such a matrix, let's say you have theta, okay, whose total variation is a bit different definition, okay? Remember, well, I multiplied by n so that now it's just this normalizing factor is gone, okay? It's simply the sum of the h differences. Anyways, whatever. So what you do is that you start with the signal, this matrix, and you go in a greedy fashion, okay? By diagonally splitting, splitting your matrix into parts until you arrive at a partition. Again, you will arrive there by means of dyadic split. So that partition would be a recursive dyadic partition, as we require here for the obtaining the bound. But what will happen is that what will ensure is that within each of the block of this partition that we arrive at, the total variation of theta, okay, would be smaller than delta. Delta is some small number that we'll choose, but forget about that. Let's say 1 over 2 or whatever, okay? And you can ensure that if you do that, it's quite easy to show that the number of partitions of such a matrix, is just the superadditive property of total variation functional, okay? It's very simple. You can show then using that, the number of blocks would be at most v over delta, okay? Otherwise, the total variation of the matrix theta would exceed v. Essentially, that's the reasoning, probably missing by a factor of log n. And, okay, and now what happens is that within each such block, your total variation is at most delta. That's by definition, that's such condition, that stopping condition. Then actually, you can use a discrete version of Gagliardo-Nierenbach inequality to say, which says that, well, if you then simply approximate theta by its average value in each of those blocks, this L2 error that you incur, total L2 error, is at most v times delta. Okay. Actually, what you incur in each such block is delta squared. Its total variation is squared. Okay. That's basically Gagliardo-Nierenbach, what that would give you. And then you just multiply it over, because it just sum it over all blocks, over that many blocks, you get v delta. As simple as that. Okay. So you just sum them over here. Okay. And you get the v over square root of n. As simple as that. So that's the proof in a sense.
There's a question about the motivation for the total variation.
Okay. So, well, it's a very Well, I think, two-dimensional images, you can imagine, for example, it is very a good, so for example, the piecewise constant functions, you can imagine like an image, there are it consists of fewer homogeneous pieces, okay? Within each piece, you incur very low total variation, and only things will come from the contribution of the boundary, and that will actually lead you this kind of functions to be a bounded total variation, okay? And this is and also this is a very popular class of functions with anisotropic smoothness. Actually, first, you'd look at this kind of thing. So you can think in a mind like, if it consists of fewer homogeneous blocks, that is actually not a very unreasonable assumption if you think in terms of image or something like that. And then actually this actually will have a bounded variation, total variation, and it's a very popular technique for image denoising. Okay. How many time do I have left? I think very few, 4 minutes, right? Okay, so let me just try to probably give us very brief sketch of the proof. And this will be probably, okay. And it's quite standard, for those who are in empirical process theory, I think, but for others, probably might be interesting. So what you do is that you just observe that both of these estimators, for both of our estimators, you can think of the parameter space to be a union of subspaces. Okay, so a union over a finite collection of subspaces. So what do I mean is that what should you think of as well, for our cases, let's say in dyadic card, one of such a subspace will correspond to one particular partition, or in the hierarchical, even in the ORT, it would correspond to a partition in the respective class. And what is the subspace? Subspace is obvious. Is a class of all is a subspace of all matrices or arrays, sorry, that are constant in the blocks of that partition, right? That forms a subspace. So that's your parameter space. So then both of our estimators are special cases of the penalized least square estimator, where you penalize the L2 distance from theta with a tuning parameter times ks theta. And what is ks theta? Ks theta is basically these functions of the versions of the functionals k all theta or krdp theta or k3 theta. Okay, so what they all are is essentially the minimum dimension of a subspace in your collection of subspaces, calligraphic S, that contains that signal. Okay, so so if you have k pieces, then it's exactly k. Okay, if the minimal partition contains k pieces, then it's k. Okay, so that's the way to set it up. And one other thing, actually theoretical assumption, and which is important for deriving our bound, and which is true in this case, is that this kind of entropy bound, which is that the number of subspaces with a given cardinality k is bounded by lit capital. And this is a very blunt bound, actually, for our crude bound. And it's very easy, right? I mean, you can convince yourself very easily that it's true, because the number of rectangles you have to partition it at k parts into each side, that is little n to the power k, and you do it in all so you multiply it d times. So anyways, it's much better than that. Okay, but that's enough. With all the assumptions, like I said in the previous slide, we have for this general class of problem the following response. Now, which you can immediately recognize how it corresponds, how from this, we can obtain our two responses. Okay. So let me just give you a brief hint. How is it done? Okay, I'll not bore you much. So for this, let's assume that your noise entries are all Gaussian, standard. Okay, Gaussian. Well, you do the obvious thing is that you use the fact that theta hat is the minimizer of this objective of this function. So you just use that and you expand. You substitute y, theta star plus sigma z for y, and expand. Just do standard manipulation. Okay, after expanding the squares, and you get these two terms. So the first time you can recognize that it just only involves some theta, this theta. It doesn't involve theta hat at all, so you can take an infimum over that. And the second term, for which actually, so this will contribute to this term, and the second term is for which you need to obtain this sigma square, this constant time sigma square apart. And actually, it turns out to be more convenient to have this normalized. So that's why you do some trivial, like standard manipulation to come up with a quadratic version of that. But don't bother. So essentially, there's a quadratic kind of version of that. So that's what you have. That's actually what you want to bound, where the bound means normalized. Okay. Well, why would you expect this to work, right? Why would you expect this to be? Well, this is a linear, extremum. This is a kind of like extremum of a functional linear functionals, probably of Gaussian variables. So you have standard puris. So here is what you do. But there is still allowing theta hat, but you don't care. You just write it in a double, like triples. You just do supremum over all possible choices. So in particular, you take a supremum over. So you fix one of the dimensions. You take maximum over dimensions. You take maximum over all subspaces that lies in your collection. That contain theta hat that have dimension k, and then you take the supremum over all vectors in that subspace. Okay. So it's evident, bluntly smaller than that. And why would you expect this to be well behaved? And what is the role playing there? This comes from this, and you can actually check it. It's by basic linear algebra and Cauchy squares inequality. You actually can show that. It's very easy to show that using quadratic forms of variables, that this expected value of this quantity is square root of dimensions. So the square of this behaves like the dimension of the cardinality, which really balances this thing, right? So which will be balanced, offset by this factor k appearing here. And then this is the only place actually in this here, actually I use Gaussian concentration inequality. You just can use that to go to a tail bound around its expected value. Okay, that's okay. So we still have two supremums to take care of. Well, you just take a double union bound. That's what you do. Sum, and then you take NKS. Remember, NKS is basically this thing, the number of subspaces of a given dimension. Okay, and here actually this thing is going to come into play, and you will see why actually we should choose lambda as I said in the result. So, well, just recall that I can log of NKS by our assumption is n to the power k. NKS is n to the power k, so you take the log, so it becomes like little k times log n. So you incorporate that, you subsume that within the exponential, and what you have to beat it, this term. So this will introduce a k log n term. You only have this lambda k term to beat it, and you really want to beat it. Then it's just done. You just do an integrate, and voila, there you go. So for that, you can easily see that your lambda, okay, when you subsume it, it will give you a term like k sigma square log n. Your lambda has to be bigger than c sigma square log n, just to beat it, and there we go. So that's the origin of the lambda, nothing more mysterious than that. So just I conclude, I think I have taken already more time. So there is an open question, which is I'll just keep everything that we still like, the lambda depends on sigma square. It's still desirable to obtain lambda and to come up with some version so that we can choose lambda in a data-driven way. And that's actually the subject matter of our ongoing work. Okay, so thank you for your attention. I'll stop here.
Thanks for the talk. So, are there any questions? So, so just one question. So you said so there's some simple comparison after this to go to sub-Gaussian from.
I'm sorry.
So there's some simple comparison to go from here to the sub-Gaussian. So
oh yeah. Sub-Gaussian actually. So the only place I use Gaussian here is here I use. But you can actually have, you can do again for sub-Gaussians. You essentially have quadratic functions forms involving z, and you can use standard like like metric entropy bound and to standard like a chaining like a bound to obtain similar bounds. So that's not a problem. It just makes it simpler. Yeah.
There's a question from Hemachandra about the motivation for the sub-Gaussian noise.
Well, it's I mean, sub-Gaussian actually encompasses a lot of things. Much larger class of variables potential you can imagine. Well, one thing is that we could do it. So that's I think thing. And well, you can imagine probably in many cases, well, even if you are in some cases, I don't know, like binomial or binoliers, which are all so Gaussian, everything just works vis-a-vis. So yeah.
So if with somewhat heavier tail, things would break.
Oh yeah. So okay. Yeah. So from other So from if you have a weird tail behavior, then actually yes, things will be different. I think. Yeah. Okay. There things will be different.
Also the depend. So if I remember correctly, everything was for d equal to 2, and that is because of this. If you want to connect to the full k all, then everything has to be done. So this except for this CD alpha thing puts in some arbitrary dependence upon the dimension.
Yeah. So right. So that's I agree. Yes. So that thing might even depend exponentially on d, probably. So that's the thing. So that's why probably this actually. That's why I'd say I should. For moderate low dimensions, it's quite well. Yes. Otherwise, yeah.
But that's the only place which is badly dimension dependent.
Precisely. Otherwise, actually, in the computation terms, also you have at most linear actually. Dependence in the constants. That's
okay.
But for dimension trees.
If there's no more questions, let's thank Soshis once more. And we'll join in another 5 minutes. So at 7:31 again, IST. Thanks.
Thank you.
Hi, good morning, Sasha.
Hi, Devavrat, how are you?
Good. So Sandeep, I presume Sasha can just simply share his link, right?
That's right. Yeah, you can maybe test.
Or rather, screen.
Sasha, do you want to test your screen right now? Or?
Should I share my screen?
Yes, please.
Now, if I maximize, let's see if you can still see it if I maximize. Oh, maybe this is fine. I'll just go like this.
Sure.
Sir, can you make it the full screen?
I can, yes.
View. Full screen.
Full screen.
Previous one looked better, right?
No, previous one is better. Just go to the presentation mode.
Okay.
Just go to presentation mode. Yes.
Do you see this?
No.
Yeah, this is the problem that.
Yeah.
You cannot see this.
No.
No. Wait.
Is it okay if I just leave it like this?
Yeah, this is okay. This is okay.
I think so. Yeah.
Let's see this
one. So Sasha, we may wait for a few more minutes and then get started if that's okay.
Perfect. Thank you. How are you, Devavrat?
Good. I'm enjoying starting my sabbatical now. Yeah. Kind of. I will picked up reading non-technical books again.
Nice.
It's like the other day, my daughter was asking, "Hey, you get so many books. When do you get a chance to read?" And that reminded me of the joke that, well, I'm full enough to buy, but I'm not full enough to read.
What's on your list, Devavrat?
Actually, you might enjoy this. If this was in person, we would have spoken about this at length. It's a book called Gujarat Files by Ayub.
This is who?
Rana Ayub. She was at Tehelka.
Yeah. Of course, I know.
So I mean, you know the reason. You know what it is.
Banned already in India or going to be?
I think it's already banned because it doesn't portray a good picture of Prime Minister.
Yeah, I can imagine.
Anyways, okay. All right, 9:02. So maybe I should introduce and hand over the floor to Sasha. So welcome, everyone. It's my distinct pleasure to introduce my colleague, Sasha Rachlin. Sasha Alexander Rachlin, he's a professor of Brain and Cognitive Science and Institute for Data Systems and Society. We've been thrilled to have him especially in our statistics center, where he's been leading effort in a variety of research activities at the interface of statistics, machine learning, and computer science. And today he's going to talk about, looking at the title, talk about something really exciting, which is in the context of online learning. So Sasha, floor is all yours.
Thank you very much, Devavrat, and thanks to everyone for the invitation. Pleasure to speak here. So this is going to be based on work on a number of papers. So the first one is with Misha Belkin and Sash Tsibakov, and then a series of papers with my former student Tengyan Liang and my current student Shiyu Zhai. So let me start. I'm going to ask the following seemingly silly or naive question. Can a learning method be successful if it memorizes the training data? The reason that I'm asking is if you take a course in machine learning and maybe even in statistics, it's often that we analyze the performance of a machine learning method by writing the test error as the train error plus test minus train. Of course, this is a tautology, but it is suggestive that we need to balance we may try to balance fit to data, which is the first term, and then the expressivity of the model, and that's given by this difference between the test and training error. Of course, the bigger the model, the bigger is the second term, but the smaller is the first term. When we go to modern applications, this is from the Zhang et al. 2017 paper, we see that in many of the applications of deep neural networks, the model is so over-parameterized that the training accuracy, that is this first term here, training accuracy is 100%, or the error is 0. And the test accuracy is kind of far away from that number. So we don't see this type of uniform convergence of empirical and expected quantities that we, that we propose in the classical view of machine learning. So this has been an observation that was repeated in a number of papers, and in the last 2-3 years, there has been a push to try to understand mechanisms for why such a discrepancy can happen between the train and test accuracy. Just a few more results of this sort. This is from 2015 paper by Natia and co-authors. As you take a neural network and you increase the width of the neural network, so h here is the width, at some point, and this is the end of the training epoch, or end of the training process, I should say, the training error, again, is 0 after you take a model that's large enough, and that's easy to see. But what's interesting is that the test error, which is the red and blue, does not go up as you would expect from the decomposition that I showed on the first slide. So this phenomenon can be reproduced in a number of settings, not all of them, but in a number of settings in recent years. I should also say that this is actually an old observation in a certain sense. This is a paper from 1997 by Lawrence et al., where they take a network with 364 times more parameters than training points, which is not too much. It's only 18,000 parameters, but still, for that time, it was shown that as you increase the number of hidden nodes, you also have this decrease. And I will point out what is different about the 2020 versus 1997, and part of it is that these are classification losses, and the striking part is that the same phenomenon can happen in regression with noisy data. So when we turn to classical books, we do have the statement appearing all the time that with too much fitting, the model adapts itself too closely to the training data and will not generalize well, i.e. have the large test error. And interpolating fits are unlikely to predict future data well at all. So by interpolation, for the rest of the talk, what I mean is that the model, after training, reproduces the Y values within the training data set. So it memorizes the data. I will equate memorization and interpolation, although some people make these distinctions. So the classical bias variance trade-off is given by this picture. Out of sample, on the test sample, you have the red U-shaped curve. On the training sample, the larger model you take, the smaller is the training sample. And from this picture, it's suggestive that this point necessarily is to the right of the minimum of the optimal bias variance trade-off. And I guess the first point that we'll make is that this has nothing to do necessarily. The training performance has nothing to do with the test performance necessarily. And then we'll get into some more subtle results, more subtle details. Here is another one. You have to trust yellow books. So we go into the yellow books and search for these statements. On the left, you have a fit that goes through the data points. It interpolates the data, and these authors say that this may lead to a function that interpolates the data and hence is not a reasonable estimate. So we're not making this up. This is something that's ingrained in the in statisticians and machine learners kind of training. So let me say what is surprising, what is not surprising in the setting of overfitting in deep networks. So what is not surprising is that we have more parameters than sample size, and this is just called non-parametric in statistics when you have number of parameters comparable to sample size, or you can have parameters infinite, and the number of parameters is in the eye of beholder. There are different ways to define parameters. Another thing that's not surprising is that good performance with zero classification loss on training data can be obtained, and there is margin analysis that allows you to trade off the regression fit and model complexity. And in fact, the observation from AdaBoost that even after perfect fit, that was in the 90s, the margins keep increasing. That led to this large margin theory, and we can debate whether that is has some power in this particular example, but that's some explanation. Another point to make is that when the base risk is zero, in other words, when there is a perfect separator with zero population error, that's also not surprising. So we have perceptron, for instance, one of the first methods, and that perfectly interpolates the data in terms of 0-1 loss, and yet it does well on out of sample. So what is surprising is that good performance with zero regression loss on noisy training data can be achieved. This is surprising, and somehow the label noise, or the noise in the outcomes, is making its way into the parameters, but it's not hurting the prediction accuracy. So we believe that this is a new phenomenon that's not restricted to neural networks, and so the question that we wanted to ask is, what are the general mechanisms for this phenomenon? And so what I will do next is show several models where interpolation coexists with generalization in a perfect harmony, and serves as a kind of explanation, perhaps, for the mechanisms that can be that can be responsible for this phenomenon. And there are a couple of key takeaways that I just want to put on the slide before I get into the details. First one is the model simplicity is a subtle notion, and especially in high dimension, and that's something we will see later. Nonlinear models in high dimension can be nearly linear and yet interpolating, and so this picture of a highly irregular function that passes through the data, that's a very low dimensional picture that we have in our mind. And in high dimensions, things can be interpolating and quite nice, close to being linear. Another interesting thing that we'll point to is a certain implicit regularization in kernel methods and in wide neural networks, and that's due to the algorithm employed for training, and also arising from nonlinearities of the kernel function, and also the spectral decay of the data. So the bottom line is that generalization or good performance out of sample can coexist with interpolation. So we've been pursuing the following research program, where we started with local kernel methods, in particular the Nadaraya-Watson estimator. And I'll describe this very simple result, which is nonetheless instructive. Then we turned to global methods, and we looked at kernel ridgeless regression, and there has been another line of work on linear regression without kernels that I will mention as well. And there is a connection to neural networks through the random feature models and neural tangent models. And so this line of work can explain certain regimes of wide neural networks, why they provably they can be provably optimized, and they also interpolate the data, and yet they generalize. This is not all of the regimes of neural networks, but it's at least a start. So here's a very incomplete list of references. So this work started with local methods with these two papers, Belkin, Sumitra, and Belkin, myself, and Tsibakov. Then the ridgeless kernel regression was analyzed in these three papers that I mentioned before. The parallel work in the linear regression setting is by Andrea and his group, and Peter Bartlett, Phil Long, Gabor, I think, who is here, and Alex Ziegler. And there is a follow-up paper by Bartlett Ziegler, and several other papers. So I will not go into all the details. And so the connection to random features and neural tangent approximation can be seen, and I will mention this at the end, and one can look at these papers for reference. Okay, so before I dive into the details, let me just make one technical comment. So the bias variance decomposition that's often studied in machine learning is of the following flavor. I didn't define these notions, but let me just describe. The bold L is expected risk of a learned function f hat. So this is out of sample error. And when you compare it to the Bayes error, to the best possible over all functions, over all measurable functions, we typically split it into the estimation error and approximation error. This has been at the heart of machine learning since the work of Vapnik. The reason is that the estimation error can be analyzed using uniform convergence results over this class of functions f. And the rest is an approximation error, how well this class f approximates the Bayes error. So this is a type of a bias variance trade-off, but there exists a different bias variance trade-off, bias variance decomposition, that's often studied in statistics for square loss in particular. It can be written in the following form. The excess loss, okay, I put expectation here, but it doesn't matter too much. The excess loss, the loss of the model minus the best possible, can be written just as the expected L2 norm with respect to L2 P, underlying measure. And that can be split into two terms. One is the variance term, and one is the bias term. And so we will study this type of decomposition rather this type of decomposition, because the first type of decomposition leads to these questions of uniform convergence, which we don't expect to hold, because for the model that we learn, empirical is 0 and out of sample is 10%. So we don't expect this path to actually yield any results. But interestingly enough, this path can yield results. And so here in the second decomposition, a trade-off is often parameterized by a tunable parameter of the procedure. And I'll present two flavors of the results. One is where one can interpolate the data and that parameter can be tuned still optimally. And then I'll turn to examples where there is no parameter, and still, because of some implicit regularization, both of these terms can be small. Okay, so first result is a very simple, almost I teach it in half of the class. This is another Watson estimator. So it's defined as in a closed form as sum from 1 to n. You have n data points. The data points are xi, yi. Yi is a real number, and so we define the function as just the weighted average of the yi's with functions of the following form. Wi of x is some kernel k parameterized by h of the difference between x and xi. So you can think of nearest neighbors, but this is a generalization of nearest neighbors. Right? The function k can be a box, can be a Gaussian kernel, and this choice has been studied quite a bit. So what we have on the left, and I'm just going to sketch first visually what's happening, and then I will go into more detail. What's happening on the left is a Gaussian kernel, and then we vary the choice of h. As you take h, if h is very small, that is not a good choice. It interpolates the data, but it provides no averaging. What you would like is that these functions gather locally, weigh the y variables locally, and produce a nice smooth solution. And so probably in a stat class, I would say that H 0.05 maybe in this case visually is a good choice, or maybe 0.1. And then you over smooth, right? This is an over smooth solution probably. Now, it turns out, and this was noted in the paper by Devavrat et al. In I think 1997 or 1999, that if you take a kernel that's singular at 0, then this weight becomes 1 at the point in the data set and something else outside, right? So the point is that if you take a kernel that's singular, it goes to infinity at 0, then it will always interpolate. And so the solutions that you get are kind of like this. And it has an interesting shape. It does the averaging because of the tails of the kernel, but it also has these spikes because of the singularity at 0. And so what you get is a solution that is smooth plus spikes, and so we can call it smooth, spiky smooth surface, if you wish. While for this kernel, visual inspection can tell you whether you're under smoothing or over smoothing, it's not possible to deduce that from just looking at fit to data, right? So the values on the data set tell you nothing about whether you over smooth or under smooth. So the spiky surface leads to benign overfitting because the effect of the noise is localized, and the bias variance trade-off exists in harmony with interpolation. So more precisely, we can take the following kernel, which is just 1 over x to some power, where the power is less than dimension over 2, and truncate it at 1. And then with this kernel, the result is that for beta holder true function f star, we can estimate it at the minimax rate 2 beta divided by 2 beta plus d. There are some assumptions that I didn't spell out, but they're relatively mild. And the interesting thing is that the f hat is interpolating. Okay, so the summary is that fit to data doesn't necessarily say anything about overfitting or bad out of sampler performance, and the data fitting part, which is governed by the behavior of the kernel at 0, the height at 0, is completely decoupled from the bias variance trade-off. Right. So in that picture where you have a U-shaped bias variance trade-off, and then the empirical fit to data, the empirical fit here is always 0, is always perfect. And so you can say, okay, this is a very silly example because you can take any estimator, and that's probably what many of you have been thinking. You can take any good estimator and put delta functions at training data, and then you don't pay for those delta functions in the L2 population loss because you don't get, unless the distribution has atoms, you don't pay for the behavior of the estimator at the training data, right? Because you get tested on points outside of the training data. And so you can always construct such an example, and that's true. And what is interesting is that in the examples that we'll show next, you have much more subtle behavior, but still the idea is very similar. You have a smooth part, which learns the phenomenon, if you wish, and then there is a spiky part which interpolates the data, and so this raises the kind of the possibility as a hypothesis that neural networks somehow also have such a phenomenon. They also have the following behavior, that you have a nice part and then spiky part that interpolate the data. Now, the spiky part might be important because of computational reasons, because we, to find a good model with a good fit to data, we need to make sure that the landscape, the non-convex landscape for neural nets is is tractable, and that appears to be the case when you overparameterize. So this overparameterization leads to good optimization and produces this spiky behavior. So that's the hypothesis. Okay, so I've described the kind of a very simple, even silly result for the Nadaraya-Watson estimator, and let me now turn to kernel methods, which are more interesting. So here I will talk about minimal norm interpolation, kernels and neural networks, and I will talk about kernels in 3 regimes. Then I will talk about linear regression, which is due to work by other people, and I'll conclude with wide neural networks. So we were motivated by this paper by Misha Belkin, who showed back a few years ago that that kernel methods have many of the same phenomenon that are attributed to neural networks in terms of generalization despite overfitting. And so this paper urged the community to try to understand kernels before trying to understand deep learning. And so I will talk about the 2 methods which are minimal norm interpolations. In the linear case, the minimal norm interpolation in the overparameterized regime, where the number of parameters d is more than the data size n. In the linear regime, this is just the best w, so the w that fits the data and has the minimal norm in that subspace. In the kernel case, we lift the data into an reproducing kernel Hilbert space by mapping x's into features phi of x. And we choose the minimal RKHS norm solution that interpolates the data. And if this RKHS space is infinite dimensional, which is essentially the same as taking infinity here for D, it's clear that you can always find such a solution.
Sasha, if I
Yes.
may interrupt, I think
Yeah.
David has a couple of questions in the chat. I can read it out for you.
Yes, please.
Is it possible to empirically see this in neural networks? I think it pertains to the previous slide, if I'm not wrong. And now his next question is any norm here?
Great, thank you. These are great questions. So I will show some empirical evidence, and there are papers. Let me postpone that, and I will try to answer. In terms of the norm, we will consider L2 norm, Euclidean norm here, and this is the RKHS norm. And the reason that we consider L2 and RKHS is that gradient descent on the square loss objective converges to a minimal norm solution. And so it's natural to study this, this W hat. And in the same manner, for wide neural networks, randomly initialized with a special kind of scale of initialization, gradient descent on those wide neural networks also converges to a minimal norm interpolant, where the norm is an RKHS norm with respect to a neural tangent kernel, NTK. So these choices of these methods are not ad hoc. They do come from certain basic considerations. Now, in terms of the empirical observations, let me just postpone that for a little bit. Okay, so what is interesting is that in the case of Nadaraya-Watson, that result was optimal for arbitrary dimension. So in other words, as long as you take the kernel to be of that form that I presented, and with a power that's below d/2, you get, for any dimension, you get the minimax optimality. Interestingly, for these methods, consistency of these or goodness of these procedures is really due to high dimensionality. So high dimensionality is necessary in linear and kernel regression to generate a benign spiky surface, which was not the case with the local method. And so what I will show these new phenomenon of implicit regularization, because there is no explicit regularization except taking the minimal norm interpolant. Okay, so another motivation for studying this minimal norm interpolant is, if you haven't seen this, if you do consider kernel regression, that's the best fit to data in RKHS plus a regularization term, the conventional wisdom is that you should choose a non-zero regularization. However, it has been observed, and we've run these experiments ourselves, for certain data sets, if you let lambda go to zero, either arbitrary close to zero or equal to zero, you only improve performance out of sample. So it seems that it's not necessary for all the types of data that you need to regularize. And so the interpolated solutions are those for which lambda is equal to 0 plus, right? So it's a limit from the positive side as you let lambda go to 0.
Sasha, another question by Alka, a sequence of them, as I'll ask quickly. How multicollinearity can be solved by ridge regression, as high dimensionality causes multicollinearity?
So because data are random, we can just talk about the subspace spanned by the data, and if the dimension is large enough, we do interpolate and we choose the minimal norm solution. So I don't think that's necessarily a difficult distinction. Thank you. So let's see. Right. So there is still simplicity that's enforced by minimal norm interpolant of the data, right? Even though we don't regularize it explicitly, among all the solutions that interpolate the data, we take the one that has the minimal norm. So there is certain Occam razor, if you wish, still enforced. So it's not crazy to think that this could work. But the solution can be very spiky in the sense that the norm, RKHS norm of the solution can be large. Okay, and I mentioned the other two. So first is the I want to substantiate the statement that there is something interesting about high dimensionality of the data, and what I will present is a lower bound for a particular kernel. Although I don't think there is anything too special about this one. We take the Laplace kernel, and the Laplace kernel will be defined as e to the minus L2 norm of the vectors without the square. So it's not a Gaussian, it's Laplace exponential kernel with bandwidth sigma. And the theorem says that in small dimension or in constant dimension, for no matter how you choose sigma, the lower bound is constant. So you do not have consistency. As n increases and dimension is kept constant, we do not have consistency of the minimal norm interpolant. And I guess I should have made more put more quantifiers here. The result is that with high probability, no matter how you choose the bandwidth, even adaptively given the data, even if you choose this bandwidth based on the data, you still cannot get close to the regression function, right? And so the interpolation with Laplace kernels doesn't work with constant d. And another interesting point is that the Laplace RKHS resulting from this Laplace kernel is very similar to the NTK, the neural tangent kernel space, as shown in these papers, has very similar eigenvalue behavior and eigenvector behavior. Okay, so what's the idea of the lower bound? Well, it's actually very simple to draw. and will give you some intuition for why it fails. So we're putting this type of Laplace bumps right at data points, and now if sigma is large, so the solution is more smooth. The f star is the true function. We are interpolating the noisy data point, right? Now there is all this volume here that we are paying for in terms of L2 distance between the f hat and f star. This is unavoidable for large sigma. So that proves kind of visually shows visually why this is a bad idea for large sigma. Now you can say, well, what happens for small sigma? Well, for very small sigma, these become more like a delta functions, right? It drops to 0. In fact, for any sigma, this is a solution on a real line. In one dimension, this would be a solution of a rope hanging from these points. And the behavior between points is only determined by the heights at the 2 points, adjacent 2 points. So here it just hangs down and goes to 0. And so you pay here in terms of L2 distance. And so the point of the proof is to show that these overlap, these regimes overlap, and so you cannot tune the bandwidth to get anything as n goes to infinity. You do not get consistency. And this holds for arbitrary dimension as long as dimension is held constant compared to number of data points. So if minimal norm interpolation succeeds, it has to be in the high dimensional regime. Okay, then it's natural to study at a high dimensional regime, and we'll start with not in the order of kind of historical how we derived these. We first derived the d proportional to m result, but I will first present the newer result where d is proportional to n to some power. The power is between 0 and 1. And here we find something quite interesting. So the upper bound, okay, this is not a lower bound and it's not exact behavior, but the upper bound on the risk that we find for the minimal norm interpolant, where the risk is defined as the L2 distance between f hat and f star, right, the excess loss with respect to square loss. It has the multiple descent shape. So if we parameterize the picture as d is n to the alpha, as I mentioned before, and on the y-axis we have the rate, how good the result is, the upper bound. So the rate is n to the minus beta. Then we have the following oscillating behavior where we do not get any result at 1 over the integer power, and we get good results, or the best results are on the log scale between the two powers. So in between these powers, right? So there are a couple of conclusions. One is the minimal norm interpolation in higher dimensional regimes can succeed, provably with some rate that goes down to 0, unless we are close to these 1 over the integer powers. You can say, well, this is an upper bound, and so this might not be the real behavior. And I will show that empirically we do see this type of non-monotonic behavior in the risk as we increase the number of data points. So I will present just a one slide sketch of the result, and then I will present a 3-slide sketch. So what's behind this result? Well, we consider the inner product kernel, k of x prime, which is some function of the inner product divided by d. So it's natural to scale the inner product by d to make it more like x's are on the sphere, if you wish. Now coordinates of x will be independent, And some kind of assumption of that form is necessary because we know that for low dimensional we shouldn't expect the result to hold. So it has to be a high dimensional phenomenon. So some independence of the coordinates has to be there, some form of independence. Now we assume that the function h has this expansion. And let's define the empirical kernel matrix as 1 over n k. This should be little k of xi, xj. And the idea that will be repeated in several other slides is that we consider the smooth and spiky part. We consider the signal, so to say, and then the spike that allows you to interpolate. So you can think of decomposing this matrix K into 2 matrices. Now this is a random matrix, random kernel matrix K. And the truncation will be given according to the degree of this function H. So once you decompose it into these 2 parts, one can show that with high probability, the least eigenvalue of this truncated matrix is at least d to the minus iota. So if you truncate at degree iota, then all the eigenvalues are lower bounded by d to the minus iota. And also for the tail part, this is a much simpler bound, that's 1 over n. And so with some work, after we've established this, you can show that the L2 risk, the closeness of f hat and f star, is driven by 2 terms. One is d to the iota over n, and then the other one is n over d to the iota plus 1, and that gives that that shape that I showed before. Right? You have good performance at when n is exactly at d to the iota plus 1/2, and there's some kind of implicit regularization between these integer powers because we didn't do any explicit regularization. Right? We didn't regularize the problem. We just fit the data and took the minimal normal solution. Okay, so let me go into some more details on this. I guess I have maybe 10-15 minutes. So just briefly, what are we going to do? So we're going to write out the kernel matrix, each entry of the kernel matrix. We'll just plug in that expansion of the function h, and let's just expand it out. You get a bunch of binomials with coefficients, and R is the multi-index here, and the norm of R is just the sum of the R's, right? So this can be written in. Okay, so now we can truncate this expansion and consider the truncated kernel. It's the same expansion except we go to just the iota for the degree, and we can always write this kernel as a product of features, and so this also has the truncated kernel has a product of feature representation, phi transpose. So you can think of the data from the original data matrix X as being transformed into these polynomial features, where the features are now in the dimension d choose I, roughly, right? D choose I, or d to the I, if you wish to round up. So d to the I features, to get a lower bound on that eigenvalue of the minimal eigenvalue of that kernel matrix, we would have to study this random feature matrix, random kernel matrix. So here's the theorem. It says that under some weak assumptions, we don't even need sub-Gaussianity. We just need for each coordinate to have some polynomially decaying tails. With high probability, the kernel matrix truncated at iota has, as I mentioned, d choose I non-zero eigenvalues, and all of them are larger than d to the minus iota. And the range of this empirical kernel matrix is the range of the span of the of these multivariate polynomials with degree bounded by iota. So this theorem gives you this what Andrea Montanari calls a staircase phenomenon. So you have increasing lengths of eigenvalues, which are smaller and smaller, right? So there is a step of d to the iota eigenvalues. Each one of them is d to the minus iota. And then the next one is smaller, but there are more of them, and so forth. Right. So this gives the structure of the eigenvalues of that random kernel matrix. And let's see, maybe I should skip this quickly. So these features are hard to analyze because of correlations. As you can see that just from the definition, there are lots of correlations. What we do is we do Gram-Schmidt orthogonalization process to change the basis. Once we change the basis, we consider new features, psi, and these features are weakly dependent. So we can show that these features are more tractable, and so with this feature representation, it's easier to show a lower bound on the smallest eigenvalue. And this process, importantly, that this process, the Gram-Schmidt process, has a bounded operator norm, and so you don't disturb the eigenvalues in this Gram-Schmidt process. So this is a genetic procedure for changing the basis and looking at better features for our problem. So we don't have to consider specific Gaussian random variables and do the usual Hermite polynomials and stuff like that. The result uses the kind of the techniques from small ball method, which were pioneered by Kolchinsky and Mendelssohn. So if you can establish a comparison of the fourth moment and the second square of the second moment, then we can establish essentially a lower bound on eigenvalues using the techniques similar to Kolchinsky and Mendelssohn. Okay, so let me go forward. So the bottom line is that I'm just informally stating this: the variance of the estimator is bounded by this d to the I over n plus n over d to the iota plus 1, I should say. And under suitable assumptions on F star, the bias is also dominated by the variance. And so you have the bias variance decomposition where both terms are dominated by this expression that gives that upper bound. Okay, so that's a very quick summary of the techniques. And please look at the paper for the details. Now you can say, all right, these are upper bounds. They might have nothing to do with empirics. And so interestingly, we do find this empirical evidence of multiple descent as we increase. Sorry, the axes are not labeled, but here we increase the number of data points, and we see that indeed at predicted vertical integer powers, or one of the integer powers, we get a spike up, maybe not as high as the prediction, but the places are correctly predicted where the spike should occur. And okay, we don't have at the moment a lower bound that shows that we should have these spikes. That seems to require some interesting random matrix theory that maybe someone can do. But yes, so since this work, there have been papers, some of them from Harvard, showing that in neural networks you have the same non-monotonicity phenomenon, that as you increase the number of data points, the out of sample performance has these alternating up and downs in terms of behavior. And this is very counterintuitive, because you think that the more data you have, the better the result should be. But it's not the case for these minimal norm interpolants, because the conditioning of the matrix changes with the number of data points. Essentially, the idea is I can briefly describe the idea. when n is equal to d to the iota exactly, you can it's the same situation as if you had a linear regression with the number of parameters equal to the number of data points. So here the number of parameters is d to the iota, where iota is the degree of the polynomial, right? The d is the dimension of the data. And so you cannot do anything, right? And if d is equal to if p is equal to n in a statistical sense, you're in trouble. But then as you start getting more and more data, you're able to sketch those first d to the iota directions better and better, right? Just as the classical statistics would say, you get more n, larger n for the same directions. But then you also at some point start to get new directions in the data given by the degree iota plus 1 of the polynomials. But you cannot reliably sketch those directions. You cannot reliably estimate those directions. And so you start paying for that in variance. And so that leads to the spike up. And until you pass that spike and you have enough data to estimate all those d to the iota plus 1 and so forth, right? So there is some intuition for why this should be the case. Okay, so this is the multiple descent picture. What I described so far is the alpha equals to 0 is this point where you cannot do anything, at least if you keep d constant and let n to be infinity. For the Laplace kernel, you cannot do much. And then I described this upper bound of this shape. And I was planning to also describe the d equal to n, where there is some interesting implicit regularization. So let's see if I can do it maybe in 1 minute. D proportional to n regime. So the idea here is the following: in this n equal to d regime, this is the closed form solution for the minimal norm interpolant. It's the k, the x. This is a vector of x with every element of the data set, and this is the kernel matrix inverse, and then this is the vector of y's. And what we noticed in 2018 is that if one uses random matrix theory developed initially by El-Karawi at Berkeley, then under mild conditions, the behavior of this kernel matrix is similar to linear plus ridge. And it's a high dimensional phenomenon when n is proportional to d. And so if you replace this kernel matrix by this one, you can see that there is certain similarity to implicit regularization driven by this curvature of the kernel function. And so one can define effective dimension, but let me actually not present these results because Andrea Montanari and co-authors have stronger results now that are on archive. This is Hasty et al. Paper. And so let me just say that there is some interesting implicit regularization happening due to the curvature of the kernel and decay of the eigenvalues. Let me briefly mention a very interesting line of work on linear regression by Peter Bartlett, Phil Long, Gabor Lugosi, Alex Ziegler. And so this is a linear minimal norm interpolant in d greater than n regime. And so you can say, okay, this already subsumes the kernel case because, well, you can take d to be that effective dimension or that dimension of the kernel space. What is different is that here these papers assume sub-Gaussianity or independence of the coordinates, and that doesn't hold for the kernels because the kernels multiply these coordinates together, and so just the assumptions of this do not immediately translate into the assumptions in the kernel case. So just very briefly, we have a very similar phenomenon. You can take the data matrix, and let's just assume for simplicity that the covariance matrix is a diagonal, the population is a diagonal. And you can split it into the signal part, the smooth part, and the spiky part. And I'm calling it spiky, even though, of course, these are just, of course, this is just linear, but it does have the same intuition that the tail part, the tail of the data, in certain regime can act as scale of identity. And this is given by this lemma appearing in Bartlett-Long-Lugosi Ziegler, that all the eigenvalues are sandwiched between sum of the tail eigenvalues minus lambda k plus 1 times n, below and above, up to constants. And so if you choose k such that the sum of the tail eigenvalues is larger than n times the kth eigenvalue, or k plus 1th eigenvalue, if there exists such a k, then both sides are sandwiched, and you do have this gamma, which is a provides implicit regularization, and it's the sum of the tail eigenvalues. So if you have features that decay, that the eigenvalues in the population decay at a certain rate, not too fast and not too slow, then you can expect this implicit regularization to appear. And I'm happy to answer a question. So let's see, how much time should I should wrap up probably?
Yeah, I think so.
Yeah.
And
Okay.
there are two questions from Devavrat that are waiting, and I thought I didn't want to interrupt. So maybe you can take at the end.
That sounds good. Yeah. So let me just say that just one last minute is that how is this connected to neural networks? Well, so take for simplicity one layer neural network, one hidden layer neural network. Then if you randomly initialize and keep randomly initialize these directions W, this is a random feature model where you only optimize over the coefficients of this top layer. And this is the neural tangent model where you work with the gradient of the gradient of the features provided by the gradients. And so one can relate an optimization path in neural networks to these two classes, and that gives rise to this kernel, which is called the neural tangent kernel. Okay, so that's all I want to say. The bottom line is interpolation can coexist with generalization. We found several interesting new implicit regularization methods that seem to guarantee good out-of-sample performance despite interpolation. And I guess just model complexity is a subtle notion. So you can. I was always unsatisfied when I was learning machine learning and statistics that some Occam razor was postulated as taking the simplest model, but then it was always in terms of regularization. And here you can see that simplicity can be enforced even though you go through the data points. Thank you.
Thanks, Sasha. So there are three questions I have. So I'm going to read them one by one, and then maybe and there's one more, or maybe, yeah. Okay, so let me start before it starts getting longer queue. So Dave, this question is, conventional wisdom is that there are no spikes for neural networks. The loss goes smoothly down with increasing data. And another question from Devavrat is that even for the simple one-layer wide neural network used in tangent kernel papers, do we have the spiky behavior?
Right. So the first question was I understand the observation that empirically, as you increase the number of data points, you have a steady decrease. possibly I haven't done those experiments, but there are papers that suggest otherwise, at least in certain regimes. So I should say that these results are very particular. It could very well be the case that under some mild additional assumptions, these bumps disappear. So it's very well possible that we don't, in many situations, we wouldn't see those bumps. And what was the second question? Is for NTK, whether we have the spikes. So the NTK is a particular kernel. It's an inner product kernel, except it also depends on the norm of the of x and x prime. And for that kernel, the same result holds in terms of the multiple descent, at least under the assumptions that we have. And so, at least in theory, okay, these are upper bounds, so we don't know whether they are truly there, but I do believe that some kind of non-monotonicity is expected. I should also say that the results by Peter Bartlett and Gabor Lugosi, you can engineer any type of landscape for the bias variance. It can have arbitrary, almost arbitrary behavior if you let me design the population distribution. Whether that is true in distributions that we encounter in practice, I don't know.
And maybe one last question by Manjunath. Thank you for a very nice talk. Is there a similar theory for recurrent neural networks?
Is there a similar theory? If I understand correctly, the question was about this. So this slide, I went very quickly, but there is at least in wide neural networks, and this can be multiple layer, fully connected neural networks, there are results that show that if you take width large enough compared to the number of data points, and randomly initialize, and you start the gradient descent or gradient flow, then you converge to a minimal norm interpolant solution with respect to this neural tangent kernel. So all the results that I've mentioned before about kernels apply to these models.
All right. Well, Sasha, thank you, and thank you, everyone. And I think I know this is the Sandeep. What would you suggest in terms of the next thing?
So you mean tomorrow?
Yeah, is there any announcement we need to make here, or?
A small announcement that we'll be starting an hour later tomorrow. So we start at 6:30 in the evening. We have a couple of talks, and then we break for dinner, and then we have a late night talk tomorrow.
Okay. All right. Okay. Thank you. See you, everyone.
Thank you, Sasha.